So for today, we're going to be doing a lab that's just about the relationship between force and distance, okay, when we're stretching a rubber band. Now, if I stretch a rubber band, what have I done? Don't say stretch the rubber band. Work, okay? Because in stretching a rubber band, I exert a force over a distance, and that puts elastic potential energy into the rubber band. Okay, so that part we're familiar with, but what we're going to do is see if the relationship works the way we think it does on a graph. Okay, and that is that it's linear.
Is this one posted in Google Classroom yet?
I think it is. Is it not showing up? Okay, hang on. Okay, so now that that's fixed, okay, we can talk about what we're doing in the lab. So in this lab, we are going to be putting a rubber band between the legs of two desks. Okay, and those legs will be one of the back legs of one desk and one of the front legs of another. You will need to take the little tennis ball cushion things off of there because we want them to get into the little articulated feet, like the little gaps in the feet. So, okay, we want the rubber band to go right in here. Okay, that gives us the best kind of hold on there, okay, for that. So it would be the back leg of one, the front leg of another, and you're just going to space them so that the rubber band is just taut. Okay, so it's not hanging loose, but it's not stretched really hard. We want it just taut. Okay, that's where we're going to start. You're going to put your ruler on the ground underneath the rubber band. Okay, and you're going to put it so that the zero, okay, at the very end, is right in between the front of the rubber band and the back of the rubber band. Okay? So if you're looking down on it, okay, if this is the front of the rubber band, that's the back of the rubber band, your ruler is going to go right there, smack in the middle between the two. Okay? Now, in this lab, we are going to determine the distances to which the rubber band is stretched. We will be measuring the responding force for those distances. Okay, I'll say that again. We, as the experimenter, are selecting the distances, and then we are going to measure the responding force with the spring scale. Okay, this is a spring scale. Now, our spring scales suck because they are not what we ordered. Okay? The ones we ordered are supposed to have newtons on one side because newtons are the units for force. And oddly enough, the boxes they came in show that spring scale. What is in the box is not that spring scale. Not one of them has that on it, even though every single box shows the picture of what we ordered. And apparently, the customer is not always right. Because when we called up Northwest Scientific and said, hey, you sent us the wrong spring scales, they said, no, we didn't, that's what you ordered. And we said, well, we're very happy with the boxes, but now what's in them? And they said, tough luck. That's how you never get another order from somebody. Just putting it out there. If you ever run a business later, that was not the way to handle that. That cost them big. Okay? So we just need to convert, and it's super easy to convert grams to newtons. All right. So all you do is take whatever the grams reading is and multiply it, or sorry, divide it by 100, and you've got your force in newtons. So super easy. Not a source of error. Okay. You can't use that one. It's not a source of error because we are correcting it. Okay, and we know exactly how to make the conversion. Okay, so what we will do is we will attach the spring scale to both sides of the rubber band. Okay, so when the rubber band is stretched between the desk, okay, you're going to grab both sides of it and you're just going to pull. Okay, you're going to pull so that the hook gets to whatever reading it was, okay, whatever distance we had decided on. Okay, so it says the 5 centimeters. Pull it so the hook is at 5, and then take the reading off of the face of the spring scale. Okay? Then you can let it go, and then you can pull it to the next one, and read it, to the next one, read it, to the next one, and read it. And we shouldn't have too much trouble getting good readings all the way up to 15 centimeters. Okay? If, and this does happen sometimes, if the spring scale maxes out before you get to 15 centimeters, and it shouldn't, because that's easily more than 15 centimeters. And if it maxes out before that, then pick some other distances that are shorter. Okay, because otherwise it's just gonna say that everything after that is 2,000, and that's not true. Okay, it's just that's the most it can go. Okay, everybody with me on that one? Now, there are two different kinds of spring scales in the box. There are 2,000 gram ones, that's what you want, they're red, and their boxes have a little 2,000 written on them, and 500. The 500 are useless, okay, because they'll max out at like 5 centimeters. Okay, so make sure you pick a 2,000. If you pull out a scale and if a 2,000 box and it's green, somebody switch the boxes, just go get another one. Okay, so if you got a green scale, you got the wrong one. Okay, you need one that's red. All right. The other thing you need to watch for is the calibration of the scale. This little metal, silver metal piece here that actually has the readings on it can move. Okay, and so now it's saying that with absolutely nothing on here, I'm already pulling at about 2 newtons. Well, that's not true. I'm not doing that. So what you have to do is leave it hanging like this and just make sure that when it's like that, the little metal tab is right at 0. Okay, so that it's calibrated, because that gets messed up all the time. Okay? All right. Questions on how the procedure is going to work? Okay, so back to the design here. Okay, so we talked about manipulated, we talked about responding. Think about what things need to stay the same every single trial, and I'm going to tell you one of them right now. Your group is going to need to have 4 people in it minimum. 2 of those people are dead weight, and I don't mean that they're not contributing anything. I mean they actually have to sit in the desks and keep the desks from moving. Okay? Because if the desks move while you're doing this lab, it will change the initial tension in the rubber band, and then your data isn't going to be true. Okay, so once you get that thing all established, put people in the 2 desks so that the desks can't move. Okay, and then those people got to sit still for like 5 minutes, okay, so that you can get all of your data. What happens if the rubber band breaks?
Comes flying back at you.
It will, sorry. What do you need to do if the rubber band breaks besides duck? Get another one, and start over. You can't be sure that all of these rubber bands are identical. Okay, some of them may be in better shape than others, some might be newer than others. Okay, all you can do is make sure you have the same one the whole time. Okay, and then you can think about anything else that might affect the rubber band, that might need to be controlled in this experiment. Okay, those I'll leave up to you. Remember, all your variables need to be explained, okay, and identified. And that explanation is how it's being manipulated, responding, or controlled, and why. And make sure it's got that. I'm still seeing some labs where people are not doing that, and you're just losing marks every single time. All right, back to the design here for the hypothesis. Okay, so we want to generate a hypothesis that explains how, using the materials below, we can calculate the work done on an object. So, the if part, what is work? Don't tell me the formula, okay? That's how to calculate work. I want to know what is work. So if work is blah, 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 and describe the experiment. A rubber band is stretched to specified distances with its force recorded. The then part needs to tell me, how can you calculate the work? And that's why I said, don't tell me how to calculate work in the if part. Okay, I want a definition of work in the if part, I want a calculation of work in the then part. Okay, questions on that? So how long is it gonna take to collect the data for this? Like, it should really take no time at all, okay? Like, within 10 minutes, we should have everybody back at their desk, and I can start talking about what to do with the analysis. All right, because all you're doing is putting the rubber band between the desks, sitting 2 people down, and going 1, 2, 3, 4, 5, okay? And you're done, all right? It takes no time at all. So those specified distances, did we put those in, did we specify the distances in the Google Doc?
Yeah.
We did, okay. So let's just open that up so that you guys see what they are. Okay. Oh, wrong screen. Okay, so the specified distances are 0, which is easy. You don't have to do that one. That requires no force. Okay, 0.03 meters, that's 3 centimeters. Okay, 0.06, that's 6 centimeters, 0.09, and 0.12. Those are the distances. Everybody does the same distances. Okay, questions? Okay, rubber band, meter stick, spring scale. Go. So once you have your data, you're going to build a graph that looks something like this, right? And you're going to have distance on the x-axis, and you're going to have force on the y-axis. So when you put this into Google Sheets, make distance your first column, and make force your second column, all right? And then it should plot it that way. If it doesn't, call me over and I can give you a hand with it, okay? And then put a linear fit on that. It should be pretty much perfect, okay? And then we're going to be doing some calculations with that. So that's kind of the first part of the analysis, is just getting your data on the force distance graph. Okay. Now, if we go back to the analysis here, okay, it says that we can calculate the area beneath the line on a force distance graph using the equation for the area of a triangle. We already know that, but okay, yeah, it's laying that out for us. Okay, so it says perform this calculation and record the number with units. So here's where you have to do a little bit of thinking. Firstly, I need to know what the value is on the line for y at my maximum distance. Okay, I don't know what that is. I mean, I can look at my chart, but then why did I build the graph? Okay, so this is just like in the acceleration lab. I need to do a y equals m times x plus b question where I will put 0.12 in for x, so that I know exactly what y is, and that will act as the height of my triangle. Okay, so that's the first calculation you'll need to do and show me. Then you can do your area calculation. You'll know that the base of your triangle is 0.12 meters. The height of your triangle will be the y you just calculated, base times height over 2. Okay, that's the calculation you have to do. Now, in terms of units, and in terms of question number 2. Look at this graph. Look at what's on the 2 axes. Okay? When you calculate the area under this line, you are multiplying what's on the x-axis by what is on the y-axis. Think about what that calculates and what the appropriate units for that might be. Okay, and then you'll use that as your justification for analysis question number 2. Okay, what does the area underneath the force distance graph represent? How do you know? I'll want a little explanation as to why you think it represents whatever you think it represents, which I am not going to spoil. Okay, everybody follow me there. Is there very much to this analysis? Should we possibly get this whole thing done in class today? I'm hoping so. I don't want this to be homework, okay? I'd like you to be pretty close to done, if not totally done, okay, by the end of class today, because we still have quite a bit of time. Okay. For the conclusion, same as always, copy paste your hypothesis, tell me if it's acceptable or not. Okay, sources of error. Okay, think about all the things that were in your controlled variables and what might happen if maybe they weren't 100% controlled, okay, or if something happened during the lab, okay, that you couldn't do anything about or anything like that, okay, any of those things can be sources of error, right, and tell me how you would fix them. All right, questions on the expectations there? Okay, let's get to work and see if we can get it all done.